Hello and welcome to another fun-filled week of physics. This week we're talking about thermodynamics. So the first thing I want to do is just a real brief review of some concepts you learned in chemistry class, but you might not be the most familiar with at the moment, particularly pressure and moles. So pressure is, we're going to use the symbol P for it. So there's a lot of different units people use for pressure, but the SI unit that we're going to use is going to be pascals, or newtons per meter squared. All right, so how do you find pressure? What is it conceptually? Pressure is a force that is distributed over an area. And so we are actually going to use this very simple formula of pressure equals force per area. So that's why it has units of newtons per meter squared. So in the context that we're going to talk about it in is mostly going to be gases. So you're going to have a gas which is in a container. So it's going to be exerting a force on the walls of the container. And so if we add up the total force on the walls and divide by the total area, you get the pressure. Some other units for pressure that we're not going to use, but you might have learned in chemistry class, I'll just say these real briefly, are going to be atmospheres. You might have used like kilopascals some, and that's fine. It's just 1,000 pascals. And then you also probably had something like millimeters of mercury, maybe torr, something like that. But we're going to stick pretty much exclusively with pascals. Okay, so what is a mole? Well, if you ever looked at the periodic table, you've seen, let's just take oxygen for example. You'll usually see oxygen, the little box for it, a nice big O in the center, and you'll see an 8 up here, and then like a 16.00 down here. Well, this means its atomic mass, and that's its atomic number, right? And so so what a mole is a mole 6.02 times 10 to the 23 atoms, molecules, or just more generally particles. So just like a big stinking lot of particles is what a mole is. And we want this special number though, because if I take 16.02 or 16. If I take 6.02 times 10 to the 23rd particles, and I multiply it by the atomic mass, the mass of a single oxygen molecule. So maybe I should say this is 1 mole. Let's write it as, and multiply by the mass of 1 oxygen molecule, or atom. I get 16 grams. Now, why do I get 16 grams? And I'll tell you, it's not just coincidence that 16 grams and the atomic mass of oxygen is 16. Whenever I multiply the 1 mole by the mass of 1 oxygen atom, or one atom, I will get its atomic mass in grams. So that's why it's a special number. So it works for anything. So if I have 6.02 times 10 to the 23 hydrogen molecules, I will get 1 gram. If I have 1 mole of carbon, that is 12 grams. If I have, just anything you want. I can just keep naming things, and I'm just reading the atomic masses off things, basically. 1 mole of sodium is 23 grams. There's another one. So it's a really, really useful tool in a really useful number in getting things into units that we can work with. And things that we can work with. So if I wanted to figure out the mass of a single oxygen molecule, what I actually would do is I would take 16 grams and I would divide by 1 mole, or 6.02 times 10 to the 23 particles, atoms in this case, and I would find the mass, grams per atom, right? And that's going to be some absurdly small number. Let me grab my calculator. So having just put in my calculator, I am getting 2.66 times 10 to the negative 23rd grams for a single oxygen atom. Now, it's important to note that we usually do these in kilograms, so you should probably convert to kilograms. So this is going to be 6.02 times 10 to the negative 26 grams, or kilograms. Because I just divide by 1,000. And the way I like to do my units and dimensional analysis, just to make sure I have everything right, is let's say I want to know the mass of water. Let's just pick water because it's simple. It's going to be easy to do. I know that hydrogen has an atomic mass of 1 gram per mole. I know that oxygen has an atomic mass of 16 grams per mole, which tells me that H2O, water, has an atomic mass of 2 times hydrogen's atomic mass, so 1 gram per mole, plus 1, because there's only 1 oxygen, times 16 grams per mole. Oop, there we go. So this should be 18 grams per mole, right? 2 plus 16. So now if I want to figure out the mass of, let's say I want to figure out the mass of a single molecule of water. I can find them individually and add them together, or I can do them this way. So what I can do is then say I want 18 grams of water per 1 mole. So then I'm going to multiply by 1 mole per 6.02 times 10 to the 23 particles. So what I like to do is I say whatever's on bottom, I'm going to put on top over here if I'm trying to get rid of the bottom, right? Or if I wanted to get rid of the top, I would put whatever's on top down on bottom and then figure out how to cancel what I need to do. So I'm using particles. I could use molecules. So then I can cancel my moles, and those just cancel real nicely. And then once again, I can pull up my trusty calculator, and I'll pause it while I do the calculations because you don't want to sit here and watch me. So I get 2.99 times 10 to the 23rd. And I can just carry my units over. So I got grams of H2O on top. And then on bottom, I have particles. Now, what you could do, if you wanted to, you could do this all in one line. It's a little bit faster. Oh, this is supposed to be negative 23 up here. What you could do is I could have converted to kilograms in one line, or I could just take it down here. So I can say 2.99 times 10 to the negative 23 grams of H2O divided by particles. But I want to make this in kilograms. So H2O is not a real unit, it's just a label so I know what I'm talking about. So I'm just going to ignore it. Also, looks like it's kind of multiplied up here, so I could just do this anyways. So I want to get rid of grams, right? So I want some number of grams down here. And I want kilograms on top, so I'm going to do 1 kilogram. So how many grams go into a kilogram? That's 1,000. So I'm going to be dividing by 1,000. I'll get a new answer. So these grams and these grams cancel. So I'm going to get 2.99 times 10 to the negative 26 kilograms H2O divided by particles. So that would be 2.99 or 3 times 10 to the negative 26 kilograms of water per single molecule. All right. I hope this was a little bit helpful. But yeah, and I hope you remembered a few things and hope you already knew it actually. Anyways, I'll see you in the next video.